Hello viewers, we have been discussing about various types of subsystems or building blocks that you require in making an embedded system. In the last two lectures we have discussed about transducers, signal conditioning circuits. In today's lecture we shall discuss about optocouplers, DACs, digital to analog converters and relays. Let us start the discussion with optocouplers, which are essentially known as optical isolators, optical isolators or optocouplers. They are commonly called as optocouplers. Let us try to understand why do we need optocouplers. An embedded system has to interface with some noisy industrial environment. So, in an industrial environment there may be a lot of noises, the voltage levels may be different from the controller or the embedded system. So, in such a situation it is necessary to use an optocoupler or isolator. So, why do you need it? Two systems operating in two different voltage levels. So, in such a case obviously you cannot directly electrically connect them, or say environment is noisy, so you do not want to connect the ground of the environment to your system, and so that the low level noise and other things do not come to the controller or embedded system. Let us try to understand what is inside an optocoupler or optical isolator. We have already discussed the use of photodiode, and photodiode has been used in making optocouplers. Let us see how it is being done. Inside the chip you have got one light emitting diode, this is your LED, and there is one transistor, phototransistor. These two devices, a photodiode, this is your light emitting diode, and this side is a transistor. These two are housed in a 6-pin dual inline package. So, this is 1, 2, pin number 1 and 2, and usually the pin numbers are 4, 5 and 6. Now, whenever there is no current passing through the LED, no light is emitted. As a result, the resistance between collector, emitter or collector base, if it is used as a single diode, this can be considered as a, this is your NPN. So, this is NPN transistor. So, this is N and P. So, this can be considered as a photodiode, then pin between 5 and 6, or whenever it is, when the pin this is not connected to the circuit, 5 and 6 can be used as a phototransistor. Either way it can be used. So, here you have got an LED and here there is a phototransistor. How it works? So, whenever you connect one, let us assume this is connected to ground and this side through a resistor connected to a switch, and the other end of the switch is connected to say VCC. This is your switch. Now, whenever this switch is depressed, this current will flow through the LED, and whenever it is not depressed, current will not pass through it, and this side is the system from which signal is going to the embedded system. This side is the embedded system. Now, this side can be used in two different ways. It can be used as a simple diode, In such a case, this pin number 5 and 6 can be used, and whenever it is used as a phototransistor, then 4 and 5 has to be used. And there is another configuration in which these optical isolators are available. This transistor LED part is same. There is one LED, but in the instead of transistor, there is a Darlington pair of transistor to increase the gain. So you have got two transistors. This is one. This is another one. This is Darlington pair. Collectors are sorted together. It is available as separate pin, and base is all available as a separate pin like the previous case. So a light emitting diode and a Darlington pair are housed together in a simple 6-pin DIP. So here also the pin numbers can be same, 1, 2, this is your 4, 5 and 6. Now you may be asking why we are talking about 3 different uses, 1, 2, 3, 3 different uses are is photodiode, second is your phototransistor, third is your Darlington pair. What is really changing whenever we are using them in 3 different ways? Let us try to understand the differences between the two. Say whenever we are using, so this is your optocoupler, we can use as diode, we can use as phototransistor, and another is Darlington pair. What actually is changing? There is one important parameter called the current transfer ratio. That current transfer ratio is measured by CTR or current transfer ratio. CTR. CTR essentially is equal to the input current by the output current. This is your input current, the current that you are passing through the light emitting diode, and the current that is generated. As you know, a phototransistor generates a current when light falls on it, and that current will be different in case of photodiode. I mean, will not be same in 3 different cases. In case of photodiode, the CTR value is only 1 to 2%. That means if the the current passing through the light emitting diode is 20 milliampere, the diode current that will get is about 1 milliampere or 2 milliampere, which is only 1 to 2% of the input current. So this is this ratio. That means you can say it is one way the current gain between input and output. So this is expressed as CTR. So in case of phototransistor, this obviously the current will be more. It will be about 10 to 100%. That means whenever you will be using pin number 4 and 5, that means this transistor, in such a case pin number 6 is not used, it is no connection, it is not connected to the circuit, then the current transfer ratio is between 10 to 100%. Of course, it will depend on the type of transistor that you are using and the efficiency of the LED. On the other hand, whenever you are using Darlington pair, the current transfer ratio can be as high as 100 to 500%. That means if 20 milliampere passes through it, between these 4 and 5, the current that will get, it can be as high as 100 milliampere, 5 times. Now you may be asking, why not use Darlington pair always? Because you get more current gain. There is reason for that, for not using the Darlington pair all the time. The reason for that is the speed of operation. Speed of operation is fastest in this case, and in this case slowest. and here it is moderate. That means whenever you use Darlington pair, then the speed of operation, the rate at which the transfer of current will take place will be slowest in case of Darlington pair, fastest in case of diode. So whenever you want high speed, then you will go for low current to transfer ratio, but whenever the speed of operation does not matter, you can use Darlington pair. So this is the trade-off between speed and current CTR, current transfer ratio. So depending on your requirement, you can use any one of them. So we shall later on see the use of optocoupler, but before that let us discuss about another important device, that is relays, that is used in many embedded systems. Why do you need relay? There are many situations where the embedded system has to control large voltage or large current, and obviously the electronic circuitry of the embedded system, which operates at a very low voltage and low current, cannot directly drive them. So in such a case you have to use a device known as relay. What is a relay? Let us try to understand what we mean by relay. A relay is a electromechanical device and the construction is somewhat like this. There is a coil of the electromagnet, then there are contacts like this, 1, 2, and in the middle there is 1. So there are 3 connections coming out from here, and this is the connection of the electromagnet. So this is housed inside some box, plastic box. It is available in this form. Now these 3 wires can be used to control high voltage edge current. So when there is no current passing through this coil of this electromagnet, then usually this is making contact with this line. That means say this is your A, B and C. So A and B will make contact whenever this electromagnet is not energized or no current passing through it. So no current passing makes A and B contacts. On the other hand, whenever this coil is energized, current passes through this coil, then this middle conductor is attracted and it makes contact between B and C. So B and C contacts when energized. So this side can be used for making for controlling high voltage and high current. Let me illustrate with the help of an example of the use of relay. Use of a relay. Suppose you have to control one heater. Say this is a water bath, and you have to control the temperature of this water bath. This is water here, and you have to control the temperature of this. And obviously the simplest way is to use some heater to heat it up. So you can make it on and off to control the temperature. That means whenever desired temperature is reached, you can make this heater off, and when as long as the temperature is not reached, you can make it on. You can keep it on, make it on. Let's see how it is being done. So here is the relay. Let me draw the relay first. Say this is your one contact, this is central point, and this is another contact. And suppose the mains voltage is connected in this manner. So when this will contact, this will make contact, this will be current will pass through it. So these two wires are connected in this manner. So you see this is acting as a switch. Whenever the relay is energized, then these two will make contact. So this is S1, this is center point, and this is S2. Center point and S1 will make contact when the relay is energized. So this relay is housed in a box, and it is used, this connection is made, and heater can be turned on and off. Now this side obviously will require some higher current. This relay can operate at a little, will require some high current and high voltage. Say it requires 12 volt and say 100 milliampere. Obviously this voltage and current cannot be supplied directly by port line, and you will require some transistor driver. You can design a transistor driver in this way. Say you have got a transistor operating in this manner. This side is connected to ground, and you will require a diode to protect the transistor, because this is a inductive load. Whenever you put an inductive load, you will require a diode to protect the transistor. And this side is this is your plus 12 volt. So when this transistor is made on, current will pass through this coil, and this is in reverse bias mode. As you can see, this diode D1, which is connected externally. Now this line can be connected to ground to make this transistor on, to pass current through this relay. And whenever this is open or VCC, no current will pass. This transistor is off and no current will pass. So this can be connected to a photodiode. So let's assume this is connected to the photodiode transistor, and this is this ground and this ground should be different. So this is the transistor mode. This one is made no connection, and here is your LED. You will require that LED. Here is the LED, and now this side can be activated with the help of some port line. For example, this one can be connected to say to VCC, and this can be connected to a port line. So whenever this port line is made 0, the current will pass through this LED. This current is not very high, it can be 10 milliampere or small. This current will pass through it. That will energize this transistor, that will in turn make this transistor on, and this transistor on means this transistor in turn will be on, and the current will pass through it. So you see this optocoupler side, this side can be this transistor, this ground can be these two grounds can be connected together. However, this ground is this completely isolated. This can be on the microcontroller side. So this is your embedded system. On the other hand, this side is the process under control. This can be an industrial control environment. So you see how optocoupler is isolating the embedded system from the process under control. This process under control can be a noisy environment. So here you have got high voltage and other things that you want to isolate from the embedded system. And we have seen the use of a relay and also an opto isolator to do the thing. So this is an example where the use of optocoupler and a relay is illustrated. Now you may be asking, is there any advantage or disadvantage of relay? Relays are used for a very long time. These are in process control and instrumentation for a long time. These are being used, but in spite of the fact they have a number of disadvantages. Only advantage is low cost and readily available. Let us look at the Disadvantages of relays. It has got a number of disadvantages. Number one is limited lifetime. As I have told, a relay is a electromechanical device, and obviously it makes contact, so the contacts keeps on making, I mean, there is a mechanical movement, and as a result, after using it for a long time, this mechanical operation that may not work properly. So, because of electromechanical nature of the device, it has got limited lifetime. Not only that, it controls high voltage and current, and as a result there is some corrosion of contact. And after some time these contacts does not make properly, leading to voltage drop, heating and other problems. Third problem is arcing. Each time this relay makes contact and opens contact, that means when it makes and breaks, there is a arcing, because it is switching high voltage or high current, and as a result this arcing generates electromagnetic interference or noise. So, this is also a problem of relays. Then there are other problems like contact bounce or chattering. So, although this electromagnetic is energized, because of spring action, here also there is spring action, it may just like switch, it makes and breaks several times, leading to contact bounce. And finally, the main disadvantage is slow speed. It is very slow in operation. Because of these disadvantages, there was another device which was developed to replace relays. This is known as solid state relay. Some solid state relay have been developed. Solid state relay, it does not require any electromagnetic circuit. So, you will see that it is much faster in operation. Let us see how it works. Just like optocoupler, here also the isolation is done with the help of a diode, but here the diode is essentially infrared diode, IRAD. So, it also emits light whenever current passes through it. And here you have got instead of a transistor or a Darling pair, there is another device known as silicon bilateral switch. So, this is your solid state relay. Here you have got, this side you have got silicon bilateral switch. The silicon bilateral switch also makes contact or breaks contacts. So, whenever light falls on it. So, with the help of this infrared diode, you can control the operation of this silicon bilateral switch, and it makes and breaks contact, and you can usually contact AC, high voltage AC, say 220 volt or 440 volt AC can be controlled with the help of this silicon bilateral switch. For example, here the isolation between two sides can be very high. It varies from 2500 volt to 7500 volt. See, isolation between the two sides, this side and this side, is very high, 2500 to 7500 volt, and that current transfer ratio is also very high in case of solid state relays. In case of optocouplers, we have seen the current transfer ratio is relatively small. It is maximum is about 500% or 5 times, but here the current can be, for example, current transfer ratio can be very high. For example, IRAD current, infrared diode current, can be say 1 to 10 milliampere, very small, which can be directly supplied by some port line of the microcontroller. On the other hand, that SBS current, that silicon bilateral switch current, can be very high, say of the order of 40 ampere or more. So, you can have you can control very large current with the help of these solid state relays. And solid state relays are available in two different forms. One is your zero crossing, that means you will be controlling the AC signal. As you know, this is the AC signal. So the if the light is activated somewhere here or somewhere here, it starts functioning from the next zero crossing. On the other hand, there is another type where the immediate closure. In such a case, the contact is made immediately as the light falls on the silicon bilateral switch. So optically, you are controlling a silicon bilateral switch, which is some kind of silicon control rectifier or SCR, and you can control very high AC current. And there are two types available. You can choose one of the two types as per your requirement. So solid state relay are now available in variety of sizes with different current capability, and it overcomes all the limitations of the electromechanical relays, so which are traditionally used for many years, and now solid state relays are available and which are used in many applications, and which overcomes all the limitations of the electromechanical relays. So we have discussed the two important topics, the optoisolators and solid state relays. Now let us focus on the third topic, the DA converter, digital to analog converter or DA converter. What is a DA converter? As we have seen, the your microcontroller, within the microcontroller, all the operations are done in digital domain. So the arithmetic and logical operations, all the processing is done in digital domain. So it will generate some digital value to control some any circuit or any operation or any control any analog parameter. And so you require a digital to analog converter which will convert the digital value to analog form, which can be used to control some device. For example, if you are interested in controlling the speed of a DC motor. The speed of a DC motor can be controlled by with the help of some analog current. So that analog current can be generated with the help of a digital to analog converter, but that analog current will be corresponding to some digital value generated by the microcontroller. So there are many other cases like your DC motor, where this analog voltage will be necessary to control the speed of a motor to and various other control operations. So we shall study a digital to analog converter or DA converter in short, or DAC in short, digital to analog converter in short. What it does, you are generating a analog voltage V which is proportional to a digital data D, or you can write V is nearly equal to K into D, where K is a constant. What is D? D can be written as A1 into 2 to the power minus 1 plus A2 into 2 to the power minus 2 plus, in this way you can go up to n bit, say an 2 to the power minus n. So if you look at the block diagram of the analog to digital to analog converter, it will look like this. So here it will receive those digital values, say A1, A2, in this way AN, and it will generate the analog voltage V. So this is your DAC, digital to analog converter. So how it really does that operation? How this conversion from analog to digital, how this analog to digital conversion take place? It can be done by using three building blocks. What are the building blocks? Let us try to understand. You will require some resistor network, you will require some analog switches and an op amp for current summing. So, these three building blocks are required for making a digital to analog converter. This is one building block, this is another building block, this is another building block, and of course, you will require some voltage reference Vref, and you will apply your digital data to this, and voltage reference is also applied to the network. Then this output of the resistor network goes to analog switches, and this in turn goes to op amp, and op amp generates the voltage V0. Let me draw the diagram of one digital to analog converter. Let me draw the diagram of an analog to digital to analog converter, the circuit diagram. Here, let me draw a simple 4-bit digital to analog converter. Here, I require 4 resistor R, 2R, 4R and 8R. These are connected to that voltage reference. This is connected to the voltage reference, these resistors. Now, the other end of the resistors are connected to analog switches. So, analog switches have got two poles. Let us assume there are 2 poles for each switches. One of them is connected to ground. One side is connected to ground. That means depending on the value, say A1, A2, A3 and A4, the analog switches are controlled by A1, A2, A3 and A4. These values, digital data that you are connecting to the DAC, and if A1 is 0, then this line is connected to ground. If A1 is 1, then it makes contact to this point. Similarly, for this case, whenever A1, A2 is 0, it makes contact to this pin. Whenever A2 is 1, it makes contact to this pin. And these lines are all tied together and applied to one op amp. So, this is your negative input of the op amp. We have already discussed the function of an op amp. This is connected to ground, and here you require one feedback resistor RF, and this analog voltage V0 is generated here. So, the building blocks that I have mentioned here, the resistor network, analog switches and op amp, these are all here. This is your resistor network, this is your resistor network, this is your analog switches, this is your op amp, and this is the reference voltage. Let us see how it really works. Now, whenever the connection is made in this way, we can write the expression for analog voltage that is generated here in this form. Depending on whether this switch is the value of A1 is 0 or 1, the current from Vref to this virtual ground will flow or not, depending on the value of A1, whether it is 0 or 1. So, the expression will be minus Vref, since this is connected to the negative input, the polarity will be opposite to that of Vref, and inside you will have A1 into RF by R, RF by R. Actually, here it will be A1, here it will be A2, here it will be A3 and here it will be A4. I have drawn it a little wrongly. So, this is your A4 plus A1, A2, A3, A4, half the current, yeah. So, A4 plus A3 RF by 2R plus A4 RF by 4R plus A1, A4, A3, A2 and A1 RF by this is your 4R, this is your 8R. So this can be rewritten as minus 2V RF by R into RF, and inside you will have A4 into 2 to the power minus 1 plus A3 into 2 to the power minus, this is your 2 to the power, so I have put 2 here, so it will be 2 to the power minus 1, yeah. So this is minus 2 plus A3 A2 to the power minus 3 plus A1 to the power minus 4. Actually what I have done here, here I have assumed this is most significant bit, this is least significant bit, and here I have assumed MSB as the most significant bit and this one as the least significant bit. So that's why there is some difference, but otherwise it is same. So if you look at this expression and this expression, you see D, I am getting D here, and this is constant. So this can be written as, this part can be considered as K. This is your K. So we see we are able to get the analog voltage which is proportional to this digital data, and depending on the value of A1, A2, A3 and A4, we shall get the corresponding analog data here. So you can take up some values, register values, say suppose RF is 10K and R is equal to say 10K. Then what will happen? This RF and R will cancel out, and say VRF is also say 10 volt. Then this expression will become this is minus 10, V0 will be equal to minus 10 A4 into 2 to the power minus 1 plus A3 2 to the power minus 2 plus A2 2 to the power minus 3 plus A1 2 to the power minus 4. So depending on the values of A4, A3, A2 and A1, you will get a corresponding negative voltage here. Suppose you apply 0 0 0 0 0 0 0 0, then this will be 0, this will be 0, this will be 0, and only this term will get, in that case you will get minus 10 volt. That means for 0 0 0 1 you will get output of minus 10 volt by 2 to the power A4, that is 16, 1/16th of the voltage. On the other hand, whenever you apply say 0 0 1 0, then you will get minus 10 by 8, because only from this term we will get the contribution. In this way it can be proved that you will get a digital data, analog voltage which is proportional to this digital value that is being applied here. And this particular DA converter is known as weighted resistor digital to analog converter, because we are following that binary relationship in the resistor values. So we see whenever the total number of bits is large, suppose you are using 16-bit DAC. So if this value of the resistance of this is 10K, then the resistance of this will be 10K into 2 to the power 16K, 10 into 2 to the power 16K, which is a very large value. That means 64K into 10K. So which is a large value, will not get such a high value of resistance. So the resistance will vary over a wide range whenever the number of bits is large. So far as 4 bits or 8 bits are concerned, it may be feasible to get register values, practical register values, but as the number of bits increases, it may not be possible to get register values. To overcome this problem, another type of DA converter has been developed, which is known as R2R ladder network. Everything remains same except the register network, this register network is changed in R2R ladder network, and as its name suggests, we shall be using only two registers R and 2R. So, let us see how it really works. So, you will require two values of register, say this is R, we are giving an example with 4 bits, we will require 4 uh, R registers, R type registers, then you will require 1, 2, 3, 4 and 5 2R type registers, these are 2R, here also 2R, and this is connected to ground, and these are as usual connected to those analog switches which I had drawn earlier. Here also you have got 4 analog switches. Analog switches means it connects analog voltage or current. In this case, it connects analog current switches essentially. So these are as usual connected to ground. This side, this is connected to ground. This is also connected to ground, and here you have that A4. This is A3, A2, and A1. These are controlling these switches. This switch, this switch, this switch, and this switch. And these lines are connected to, in the similar manner, connected to the op amp, which is acting as a summing amplifier, as we have already discussed. This is your RF, and this here you get V0. And this is the point where you will apply your reference voltage Vref. Let us try to understand the operation of this R2R ladder network and how it really generates currents in that binary ratio. Essentially, in the previous case, what we did, the currents were generated which are following the binary relationships. Here the Vref by R, here Vref by 2R, here Vref by 4R, here Vref by 8R. So in binary relationship the currents were generated. Here also the same thing is done. Let us see how it really works. Let us assume the value that you are applying is let us assume you are applying A4, A3, A2 and A1, say 1 0 0 0. That means all these three are grounded, and only this is connected to this. So in this case, what will be the current that will be flowing through it? So whenever these three are 0 0 0, as you can see, this is connected to ground. So R and R, these are in parallel, they will form a single resistance of R. So this is in series with R, so it will make 2R. Now this is also grounded, this R and this 2R, R plus this R will make R again, and this R will be in series with this R. So this will make again 2R in parallel. So you will get R in series with R connected to ground. So ultimately here if you look point at this point, the equivalent circuit will be the resistance will come through a resistance Vref. You are getting one is connected to ground and another is connected to 2R resistance to this summing amplifier. So the current whatever is coming through this resistance is getting divided into two parts. Half of them is going through this and half of them is going through the other parts of the circuit. Similarly, whenever you apply 0 1 0 0, that time it can be seen that whatever current is coming here, it is divided into half, this part and this part. That means the half of this current will flow through this, and out of that half will pass through this, half will go through the other parts of the circuit. So we are able to get the same binary relationship current passing through this part of the circuit. So the advantage of R2R ladder network is here you have got here you require only two types of resistors, which can be made very accurate, laser trimmed, and also it can be realized easily with the help of op amp. So this is very commonly used DAC circuit in practice. In fact, it is not necessary to realize digital to analog converters with the help of discrete components. You can use ICs, nowadays ICs are available in for digital to analog converters. For example, this 1408 is a digital to analog converter which is which uses R2R ladder network, but which is available in the form of IC, and inside this chip all the R2R ladder registers are realized by using laser trimmed, very accurate, and this is a 8-bit DA converter, and here you can apply the reference voltage between 15 and 14. You can apply, one of them can be grounded, another can be applied the reference voltage, and the current that is coming, actually it is current, it sinks current. So you get a positive voltage here, and by choosing suitable reference voltage you can generate the voltage here. So this is acting as a current to voltage converter. So this 1408 digital to analog converter is very popular. This can be interfaced through IO ports, interfaced through IO ports, because it has got no necessary logic for direct interfacing to the system bus, because there is no chip select, there is no output enable, those circuitry are not present in this particular chip. However, the digital to analog converter hardware, all these R2R ladder network, analog switches, these are all present inside the chip. The op amp has to be connected externally to convert the current to voltage, and this particular DAC is low cost and widely used. However, nowadays you can get digital to analog converters which are microcontroller compatible. This AD558, as you can see here, apart from these data inputs, say D0 to D7, where you can apply those digital data, there are two more inputs, chip select and chip enable. So with the help of chip enable, you can enable the circuitry. The data will go to the circuit, and with the help of this you can select the chip. Otherwise, it will not load this bus. It will make tri-state. And here also this AD5 analog devices AD558. In this case, the op amp is also built in. Op amp built in. So this can be directly connected to the system bus. Here I have shown it is interfaced to the through port lines, but it is possible to interface this device to the system bus of the microcontroller. For example, this you can connect to the data lines D0 to D7. This can be connected to the port line WR, the WR line, and then you can use some device selection logic or device decoder circuit, and it will generate the chip select signal whenever some voltage, some address is generated. In that case, you have to apply, instead of these port lines, you have to apply some address, and accordingly this DA converter can be mapped to the memory address space of the microcontroller, external memory address. That means it will be mapped to external data RAM. So in this way, this can be interfaced to the microcontroller. However, our discussion of digital to analog converter will not be complete unless we discuss about the important parameters that you have to take into consideration while choosing a digital to analog converter. Let us look at the important parameters. Number one is resolution. So full scale can be 10 volt. With how much accuracy you can measure, that will depend on the number of bits that you use in the DAC. Say for 8 bit, the resolution will be 10 volt by 256, that is 2 to the power 8. For 16 bit, the resolution will be 10 volt by 2 to the power 16, higher, and so on. So depending on the resolution you have to choose whether you will go for 8 bit or 10 bit or 12 bit or 16 bit. These are available of the different bit capacities. Then second parameter that you have to look at is the accuracy. What is the accuracy of the circuit? Inside the chip there are many nonlinearities and source of noises, and because of this accuracy cannot be very high. So you have to design the circuit, or you have to choose the DA converter which gives you higher accuracy. In actually the accuracy should be greater than the resolution, otherwise it will not work properly. Third parameter is linearity. Because of the nonlinearity of the devices that you use in making digital circuits, as I told, you will require analog switches, you will require op-amp. These devices may have some nonlinearity, and as a consequence the input output relationship, here you are applying digital data, here you are getting an analog output voltage. The relationship should be fully nonlinear, but because of nonlinearity in the circuit, it can happen that it may be like this. So you have to see whether the circuit is linear over the entire dynamic range. Say it can be 0 to 10 volt, or it can be minus 5 volt to minus 5 volt to plus 5 volt, and so on over the entire dynamic range. Fourth important parameter is monotonicity. Monotonicity arises because, as I said, because of the nonlinearity and other inaccuracies of these component values, the input output relationship can be like this. So in which case what you are getting for two digital data, as you can see here, this is one digital data, this is for two digital data you are getting the same analog output. So this should not happen. So monotonic means it should continuously increase, but if it is not monotonic, there may be 2 or 3 different values. This can happen because of inaccuracy or of the circuit values. Then comes the quantization error. Quantization error arises because the analog voltage range can have any value between say 0 to 10 volt. But because you are representing by 8 bit or 10 bit or 16 bit of data, you are not very accurate, you are losing some accuracy. That error is known as quantization errors. Actually quantization error and resolution, these two terms are related to each other. So quantization error will be low whenever the number of bits is large, 16, and it will be large whenever the number of bits is small, say 8 bit. Finally, you have to look at the settling time. This decides the response of the circuit, how quickly you will get the output as after you apply the digital data. As you know, op-amps are not very fast devices. They will take some time to settle down to generate the corresponding analog voltage for a given digital data. So because of these analog circuits, there will be some settling time, and after some time you will get the correct digital output. So this value is also provided in the data sheet of the DA converter. So whenever you go for choosing a digital to analog converter, you have to look at these parameters and you have to see that they satisfy your requirement. And so with this we conclude our discussion on digital to analog converters. In the next lecture we shall discuss about the analog to digital converters and data acquisition subsystems. Thank you.